it's kind of difficult for me to work out when I was asked to present something on visualization. It was kind of difficult to work out what to present to this group, because visualization means a really wide range of things depending on who you are and what your research or discipline area is. And generally in this area, in the humanities, visualization tends to be around what I would call information visualization. And although I've been involved in some projects in that space in the past, I thought today I'd have to troll back over the years for things I've done. Instead, I thought I'd talk about stuff that I'm involved in right now, mostly with humanities groups at University of Western Australia. And so these are some of the people that I've just listed at the beginning that I'm collaborating with. I mean, these are not projects. The projects I'm going to describe are not things that are my initiatives. I'm working in a technical capacity, providing solutions to these projects. These are the groups and the ones, as I describe the projects, it should be obvious who is who, and I'll mention them also as I go. I've got a slight sore throat, so if I cough, it won't affect you because I'm not using this microphone, but it might bother the audio recording, and there'll be a segue to a slightly humorous story at the end related to that cough, but we'll come to that later. So when I first saw the invite, I saw that it was 2 hours. So I've got 2 hours worth of slides for you. I'll go fast. Okay, so as is obligatory with these things, I will give a very brief, one slide in fact, introduction to iVEC. I'll also talk, again, just 5 or 10 minutes on kind of what I am supposed to be doing, if you like, which is around science and data visualization. And then I'll present areas that I've been working in the humanities at UWA, and they're mostly around data capture, image capture, novel ways of doing that. It's not particularly new. People have been applying these techniques already. I guess what I'll be presenting here is the fact that we've got local expertise in iVEC on how to do this, and they're projects that are sort of relevant to the local scene. So the one slide introduction to iVEC. It's this partnership between 5 organisations, the 5 research organisations, and of course Curtin is one of those. And it's basically about, I mean, this is my definitions. You might get different ones depending on who you talk to, but for me it's about this facilitating advanced computing across the partner organisations. And that includes both hardware, so iVEC is managing supercomputing facilities, also managing visualization and data storage, but it's also equally about the expertise in the organisation. And there are these 5 programs. So some of you may know Valerie, who's the education program leader. So if you want to know about that, you can talk to her later on. There's an e-research program headed up by Valerie, by Jenny Harrison at UWA. There's an industry and government uptake by Andrew Beveridge. Supercomputing technologies, which is by George Beckett. And there's a visualization team of 3 at the moment. So this is my definition, and like I say, visualizations is a pretty broad thing, but in the science data visualization, it's really about insight, providing insight to researchers or to the public, and it's using advanced computing, often advanced computer graphics, to achieve that. And of course, my mother has trouble telling her friends what I do because even I'm confused sometimes. So this is sort of the definition I tell my mother, so she can kind of explain what I do. It's kind of an exciting area to be involved in because it requires, or often requires, quite a range of expertise. So there's obviously a lot of computer graphics involved, computer programming. Having a good foundation in mathematics is pretty useful. But then it goes into more creative things as well, sort of perception theory and computer interfaces, human-computer interfaces. So I'll just go through a couple of previous projects around science visualization, just to set the scene for what I'm often doing, and then I'll start into these 3 project areas. So this is a visualization of computer simulations in the weather area. In this case, it's a tornado. And this kind of has a lot of the characteristics of what visualization in the sciences is about. It's about this mapping of variables into graphics. And we have a language for doing that. We use color. Hot is red is hot and blue is cold, some sort of scale there. We have vectors to show directions, in this case wind directions. And we introduce balls that bubble around to introduce, I actually don't know what that is representing. I can't remember what that's about. But there's this language of how you convert variables in your simulation into graphical representations. During this talk, you'll probably see a few examples of these round images, and that might seem a bit strange to you. That's because these are used often to project into hemispherical dome environments. So if you see circular things, we don't only generate that, we generate stuff for flat screens as well, but a lot of the examples I've shown will be for domes. So another example is a very common data set in sciences, and they're called volumetric data sets. And you get these from a whole range of 3D scanners with our MRI, CT, micro CT, from the synchrotron. And this is an example of data where you have a volume of space, and within that volume you know something at every point. So in this case it's a CT scan, so what you know about is density. In other cases it's water volume. And so what visualization is about in this case is revealing the interior of these often solid objects, whether they're fossils or in this case a mummy which has never been opened. So this is currently residing at Mona in Hobart, and it's a public exhibit, but this was part of the research phase for looking at the interior of this mummy, looking at how she died, and whether there was jewellery and all this sort of stuff. So there's sort of forensic stuff that goes on there. And then this next example, which I think is the last one, it's volumetric data as well, but it's not a scan, it's not a recording of volume. It is it's a computer simulation, in this case of galaxy formation from astrophysicists at ICRA. And again, it's this mapping between what's happening in the simulation. In this case, there are three things. There's stars, which are the whitish stuff. There's H1 gas, which is red, and then there's dark matter, which is the bluey stuff. And so this sort of highlights another characteristic of a lot of these data sets, and that this is a huge amount of data here. Every time step is about 36 gigabytes, and they ran this basically from the Big Bang till present day, not saving every time step, of course. So another characteristic of what happens in the sciences is all this big data thing where you have an awful lot of data that goes into generating these data sets. But in this case, the same machine that generated the data sets was used to do the visualization, just because that was the only place where there was sufficient resources to do that. So visualization has got that word visual in it, so you might imagine that most of the time what we're doing is using the human sense of vision to convey this information to your brain. And so you might imagine that what we should be doing is sort of leveraging what our visual system can do. And so if you're sitting in your office, there are these three things that your desktop display, unless you've got a really special one, doesn't do. And they're fairly obvious when you think about them. The first is stereopsis, so we have two eyes, they're offset, we get this sense of depth. It's not hard for you to imagine that if you've got a complicated bit of geometry that you're trying to understand or a complicated process, that having that sense of depth would be a valuable thing to aid in your understanding of what's going on. We also have a very wide field of view. So if you're sitting in your office, you might be using 20 or 30 degrees of your available field of view, and the rest is just your office. Whereas if you look straight ahead and put your hands out here, you can still see your hands. So we've got almost 180-degree field of view. And so again, you might imagine there are times when you are immersed, if you are inside your data set with your entire field of view filled up, that might be a useful thing to do. And then last thing is visual fidelity. Granted, if you've got a retina display and you're sitting up close, you're getting pretty close to what your visual system can resolve. But if you've got a large one-to-one display, generally the resolution of that is much less than what you've got in a sort of what your eye can do in the real world. And so what I'm coming around to saying is that visualization is often about employing displays that make use of those characteristics of our visual system. One way of doing that is through tiled displays. That's how you get a very large pixel count, very large resolution. You stand back to sort of zoom out. And the peripheral vision is something that's done through something like an eye dome, but there's other ways of doing that as well. So just quickly, some of the tools that iVEC provide in this space is around people. So there are 3 half-funded positions at the moment. There's budget to support projects at the partners. And we have various machinery to assist in that visualization process where they will add value. And there's also various instruments that we have to solve problems in various spaces. So 2 plugs for today. The first is Digital Humanities 2014, which I was halfway down the road and I forgot to bring it, so I had to drive back and get it, or I would have been in trouble by Jenny, who's heading up this conference. So this is an international conference happening early next year. And the second plug is to Curtin, who have got a pretty exciting facility coming online, and some of you may know about this. And if you have questions about it, Andrew Woods is sitting in the audience and can field any questions you might have. So this is a pretty exciting space going in at the John Curtin Gallery. And it's going to have a number of these machines which facilitates this visualization process. And I've listed some of them there. And it's going to have, it's in a gallery area, so it's going to have 2 modes of operation. One will be a research mode, and the other one will be an exhibition type mode. And there are these various targeted applications at the moment. And I don't know if I was supposed to put the November launch date in there. I don't know how solid it is, but I think that's the plan for a launch in November. Okay, so the 3 projects, or the 3 discipline areas, 3 capabilities I'm going to talk about, as from the beginning, is going to be high resolution photography. The second one is around 3D reconstruction of objects from photographs. And the last one is in the cultural heritage space around 360 video. And for each of those, I'll show a number of examples. So starting off with sort of high-res capture. Oh, and the thing that all these have in common, I guess, or at least I'm pretending they have in common, is that they were originally developed to solve problems in other areas, in sciences or in engineering. And they are increasingly being used in a broader sense. So this is about realizing that if you want to capture something at a higher and higher resolution, if you want to photograph something at a higher and higher resolution, you can't just go out there and buy an arbitrarily high sensor camera and sensor. So we're currently limited, and that growth is quite slow over the last 5 years. And it's also quite important to realize that having even a higher and higher resolution sensor may not get you anything, because you may not be able to afford the optics and the lens that's going to go onto that. So how does one do this? It's fairly obvious. You just take lots of photos. So you want to photograph something at a particular resolution, you just scan that with a whole bunch of photographs, stitch those together with algorithms that are pretty well established in computer science, and you have essentially an arbitrary high res. So why do you want to do this? So in the projects I'm going to show you, some of them are around going and capturing imagery from sites that are hard to get to. So you can't just arbitrarily drive there and get out and capture new research data if you didn't get it the first time. So there's access, and it's kind of all of these things are kind of around. If you've got the opportunity to capture something, you might as well do it as well as you can and generate these richer research objects than sort of doing it in sort of simpler ways. So this has been used for a long time, so most of you will know what the Hubble is. And you may have seen the Hubble Deep Field photographs, which are pretty amazing because this particular section here, if you hold your hand out and imagine what 1 millimeter is on the sky, 1 millimeter square, that's what this image is. And there are 10,000 galaxies already, and they're limited in how deep they can see. So it's pretty amazing for all sorts of reasons. But this is a mosaic, whatever you want to call it, of something in the order of 300, 350 of images to form this one image. It's being used fairly regularly in optical microscopy. Again, this is a 4x4. In this case, it's the opposite to astronomy. It's down at the microscopic scale. And this is an optical microscope that takes photos in a grid, and then you stitch that together. And we're also doing work with geologists. This is again going out to remote areas. This is a 20-meter long strip that they're interested in. You can't get the camera far enough away anyway to capture the entire thing, but they also want this cross-scale resolution or high resolution so they can do cross-scale studies. And this is another way of achieving that. So the first project that we applied this to was at a place called Wanmana, which is there. People talk about Perth being the most isolated city. Well, go to Newman sometime and see what that's like. It's a lovely site. This is kind of what it looks like. And there's these two rock faces. There's not normally water there, but we were there after some rain. And they recorded something like 200, 250 bits of rock art across that site. So it was kind of interesting. For me, this was my first trip to sort of explore some of these ideas with the Centre of Rock Art Research at UWA. And I was kind of surprised that at no point did they capture the entire site. They were only ever concentrating on individual bits of rock art. So this is them clambering across rocks, and as you can see, there's places you can't get to. And strewn across this is rock art. So the technology for doing this, I guess this is the other sort of take-home message for the three things I'm talking about here, is that you don't actually need, the equipment's not particularly specialist, and there aren't huge budgets involved in capturing this sort of stuff. So the technique here is pretty straightforward. You just have this motorized rig, which is this thing here. You stick a camera on it, a lens, you choose a lens, and this motorized thing just takes all these photographs. This is actually by today's standards, this is actually a pretty coarse image. It's only 40,000 pixels across. We're currently doing them up into the sort of 400,000 or 500,000 pixels across. But this was the first sort of exploration of this sort of on-site. And kind of in a simplistic way, this is what you're getting. So you've got this really high resolution image, and you can zoom in and pan across. And essentially what I'm calling sort of armchair archaeology, where you can explore this site when you get back in the comfort of your office rather than in 50-degree heat with mosquitoes and possibly crocs for all I know. There weren't any. And so this kind of highlights what you can do, and like I say, some of the rock art here is not particularly exciting or even recognizable. This is a person's head with a ring of mini people as a headband. So this is still zoomed out at, I think, 25% of full resolution. So we did this for each of the rock faces, and then this is how people can explore these sites when they get back to their offices. This is supposed to be a turtle. I don't quite get it myself, but yeah. And of course, my favorite bit of rock art from this place were the two kangaroos mating. There are some challenges. So this is where the sort of the computer science and even mathematics aspects come into it, but certainly imaging and computer graphics, in that if you capture one of these things, you can't just save it as a JPEG, okay? Because it turns out that until you try, JPEG won't let you go more than 32,000 pixels. And the same thing goes for both PNG and TIFF. But there are solutions to this, but there's, and the other thing you realize is that you can't just arbitrarily open these things in Photoshop. Most of the imaging viewing programs expect that the entire image is in memory at once. And so if I have a 10 gigabyte image, which notionally requires perhaps 30 gig of RAM, not only don't I have 30 gig of RAM, or probably don't, but I don't want to wait all that time. So there are technologies, and this is, I'll just skip over this, but there are technologies for managing that process where you only get delivered the part of the image that you can see at the current time. And you're actually all familiar with that because that's how Google Earth works. When you're zooming around Google Earth, you don't have all the textures, you're just delivered the stuff that you can see at the resolution that you can currently perceive. So the next project was out at Beacon Island. So you can see I get around, which is one of the fun parts of the job. So you probably, as some of you, most of you maybe, will be Australians, and I'm not an Australian, I'm a New Zealander, so I didn't know anything about the Batavia when I started this, but I do now. For those of you who don't know about it, it's a pretty sad story. Look up Batavia and Beacon Island. But the bottom line is 350 or so people got shipwrecked on this island with no water, and bad things happened. To the extent that the chief conspirator kind of had this idea that a sustainable population was probably around 40, 45, and went about trying to achieve that. Anyway, that's another story. So what's going to happen on this island is that these are old fishermen huts, and they haven't been occupied for some time, and they are generally starting to fall apart. So instead of this island, which is now a reserve, starting to look increasingly like a junk pile, they're going to remove the huts. That's going to happen perhaps towards the end of this year. And the sort of the archaeology aspect of this is that it's expected that many of the graves, or where people were buried, are underneath these huts. Now, the shipwreck was back in the 1600s, but the reason why the graves are possibly under these buildings is that the buildings were built on stuff that wasn't hard coral that you could dig, and that's probably where you would dig graves to bury people. So the buildings get removed, and then a team goes back to look for some of the grave sites. So my involvement in this has been to record, or to manage the group that are recording how this island is right now, because it's going to look very different in a year's time. And so again, that involves this really high-res photography. So we stick out on one of the wharves or out in a boat, and we capture, in this case, I think this is 200,000 pixels across. And that allows you just to do these kind of ridiculous zooms in to at least those parts that you can see. And even this, I think, is not one-to-one. I think it's still another factor of 2 on that. One of the parts of this project is creating this virtual world, and an important aspect of that, which is reconstructing all the huts, putting in all the foliage, is getting good textures. And so this is going to be the basis for extracting textures, because we can take one image and that's got information about the texture, building materials across the entire range of huts. So going back to that display idea, so one of the uses of these high-res displays is for looking at this sort of information. So if you imagine, I don't actually know what the scale is, but if you imagine this on your computer screen, your computer screen is probably a little tiny 2 or 3 millimeter section of that top image, whereas on this display, which is not really a particularly high res, the Curtin, the John Curtin gallery one will have another set of these, so it'll be a 4x3 rather than a 2x3. But this allows you to explore these really high res images without having to continuously do this panning and zooming operation that you do normally. So very quickly, the last piece on this, I think, is something which I just threw in at the last minute because I did it 3 days ago. And that is applying the same techniques to sort of to photographs, or in this case, to paintings. So this is a dot painting by this artist here. And the question was capturing this at a high res, both so that we've got a digital version, but also to do some sort of forensic work on it. And the setup, like I say, is pretty trivial. This is one of the rooms at UWA. There's nothing particularly, clever here. It's all standard camera gear, standard lighting gear. And this rig does the same thing. It scans across, taking little photographs of this, which we then stitch together. And so the painting itself is about 1 meter wide, and then you can zoom in and just see this lovely, lovely detail. And so things that you just did not realize when you looked at the original painting was that it's been overpainted. So each of these rings started off having 2 colors, and now they've overpainted it with a white. And you just can't see that because even this gap here is sort of sub-millimeter in real life. So the next thing I'm going to be talking about is 3D reconstruction. And by that I mean not producing 3D objects, assets by hand, which is, of course, have got all sorts of interpretation and stuff going on, but creating them automatically from photographs of an object. And again, it's not a new thing. It's been around for a long time. In fact, some of the Australian mining industry were actually leading this field some time ago, and sort of photographing mine pits or mining operations, going back in a week's time, doing it again, and calculating volume of material extracted. And it's got a few sort of nice characteristics. This non-intrusive thing is quite important. Often with these artifacts, you can't take them away with you. You have to do it in site. So and often you can't take some of the scanning machines to the site. So there's a few reasons why we want to do this. Some of the previous work in this space has been things like this, which is so this is totally reconstructed from a whole range of photographs of this pit. There have been researchers both at Curtin, ARC, and CSIRO, and UWA doing this sort of work where you capture rock face outcrops, then apply various analysis into that. So the first kind of exploratory work in this case for me was again at Wonmunna. So this is one of the rock art sort of rock faces at Wonmunna. And again, what the archaeologists were doing there was a very traditional thing that they do. They go and they photograph these things up close. They take bearings, they sketch them, they annotate, they have a whole bunch of data that they record for each one of these things. But the idea here was to capture a much richer, so instead of photographs, to capture a much richer sort of representation of each of these bits of rock art, namely the rock that they're on as a 3-dimensional object. In this case, I've shown 5 images. I think there are about 10 in total that were taken of this structure. And then this is what you sort of end up with as a 3D model. So certainly a much richer sort of research asset to have than, if you like, a whole bunch of photographs. So this is it's not necessarily obvious, but this is a sort of a 3-dimensional computer mesh, and it's got the original images as textures on top of that. This is kind of a surprising one because this is just 3 photographs. So you don't even have to take a lot of time in some cases. 3 photographs of this particular structure, and you can reconstruct this 3D model of it. And in case it's not obvious, this is entirely automatic. There's no human intervention here except taking the original photographs. So this is, I can't help myself, but this is about 6,000 years old. So it's got to be an alien, right? So big head, bug eyes, and 3 fingers, 4 fingers. Yeah. Okay. So again, this is a project not in West Australia. This is in Hong Kong, Dragon Gardens. If anyone here is a James Bond fan, this was where about 30 minutes of The Man with the Golden Finger was filmed. It's absolutely fantastic garden area. So unfortunately, Hong Kong has pretty well non-existent heritage laws, or there's no way to really to formally say that something is a heritage site in Hong Kong. And if you have so the top image is from the movie, so this thing hasn't changed much from '74 because there's the bottom image there. And in fact, this little round thing here is where the husband and wife who developed this land are buried. But this building here is known as Development 5A, and unfortunately this is Development 5B. So there's a big push to try to preserve this, this particular site as something significant in the history of Hong Kong's development. The person who developed this land was a major industrialist from the past. And it's rated at something like a million Hong Kong dollars per square meter, which is what, 200K per square meter or something. Anyway, so the one of the activities to both convince people that this is a site worth protecting, but also in the back of their minds, if they lose, they'll have a digital record of most of the structures and sort of artworks here. So we kicked this off about 4 months ago. It's called Dragon Gardens. There are dragons everywhere. This is actually a light fitting. This is a ceiling, and the little red thing there is actually a red light bulb. So you're looking up at this. And this kind of gives you that sense of, so this is what the 3D model looks like, but there's a mesh behind it, and then the mesh is textured, and this is the final result. So again, a very rich sort of representation of this ceiling, which we hope will not be destroyed in a year's time. This is just another staircase. These are both the 3D reconstructed versions. This is just showing you the mesh over here. Those examples that I showed you there, if you imagine a kind of 2.5D, they're not a full 3D object, but you can do full 3D objects. So this is one of the little lions that's sitting in front of the mausoleum part. And it turns out it was only until after I got this back that I realized that he's actually got his foot on a little baby lion on the head. Okay. So then just the last bit of this, which will also lead into the next bit on 3D video, was a project about 2 months ago where I finally got to go bush in the outback of Australia. So this was it's a project out of the Australian National University, which is about recording the Nintaka story. So this is a story emanating from sort of it's near Ulara, sort of the border of Northern Territories, West Australia and South Australia. And just a fast forward of this story, which is not the same as sitting around a campfire with an Indigenous leader telling you, but basically the grinding stone in Nintaka's village was pretty poor and their meal was rough as a consequence. But Nintaka could hear this lovely, smooth grinding stone in the distance, so decided to go and find this nice grinding stone. Found it in a neighboring, it took 3 or 4 days walking, but found this tribe that had this lovely grinding stone. He endeared himself to the tribe, including the chief's daughter, but that's another story. And would go hunting with them, but then one day he pretended to hurt his foot, so he couldn't go hunting. Everyone else went hunting. And of course, he grabbed the stone and scoffed off with it. The villagers returned, kind of put 2 and 2 together. Nintaka's missing, grinding stone missing, so they went after him. They found him, he denied all knowledge. They persisted and eventually killed him and recovered the grinding stone. There's a lot more detail there if you hear it told properly. But the story is told across the landscape. So besides the rest of the team that were recording, video of people telling the story at each of these locations and the dances that go along with these stories at each location, I was recording these high-res images of each of these nodes. In fact, in this case, this is supposed to be Nintaka's head. I didn't say so. Nintaka is kind of a lizard. So that you might imagine with a little imagination and eye fuzziness that this is a lizard's head sticking out of the rock face. Yes. So an important part of this story is the grinding stone. So here's a photograph of a grinding stone, an example of a grinding stone. And so capturing this, so this is leading up to an exhibit that's going to be in the South Australia Museum. So part of the interest was to capture 3D assets that they could use in virtual worlds for this exhibit. So this is a grinding stone and this is a 3D reconstruction of it. But a kind of a better version is this, because although some people may see artifacts in that, that's a pretty good representation, I reckon, of the original thing. So there's the original, and there's the computer reconstruction version with no human intervention. There's a couple of other complicated objects that are part of this story, and one of them are these headdress things that they wear. So this is an example here, and they're extremely complicated. It can't be taken away, it stays there. And it would be very hard for a human modeler to sort of make a computer version of this for the exhibit. So this is the result of reconstruction of that. Now this is not perfect. There are a few sort of extraneous things going on there, but this will be sort of the first pass of something which within a human will go in and clean up the details of. This is a full 360 object. The stick in the middle, of course, is just to hold it. That'll be removed from the... So the last one is around 360 video. And in the usual... So this technology was originally developed for things like security. So you can put one of these cameras in a building, and then the person on the security desk can see everything that's happening at once in a single camera shot. There's two examples that I'll talk about. Will be, again, recording one of these Nantaka stories, and then also this Ma Meri ritual in Malaysia. So the camera that we're using, there are others. This is still about the best around in terms of resolution. There are cheaper ones, but this is pretty much where the technology is at the moment. And like I say, the main applications around security, or the main applications before the cultural heritage stuff, is about security. We've done some projects with Rio around remote operations. ECU are currently doing some work around performance of teachers in schoolrooms, and we've done some, I'll show you some orchestra sort of work in that area. And then sports science have been doing some exploratory work on using these immersive displays, which you need to capture data for presenting sports scenarios and doing evaluation of elite athletes. So this is a performance sort of evaluation. This is just a single shot. This is just to show you what comes off the camera. And if you think about what an Earth map looks like, this is the same sort of projection. You might imagine that if you walk off here, you come in here. I don't know if you can see anything wrapping around, but that's the end of this structure here. So the camera is capturing 360 degrees. It's capturing it at pretty high resolution as a video stream. And then the North Pole is stretched across the top, so that's why it looks distorted. But then if you look at this in the correct way, it doesn't look distorted. It looks quite natural. So one of the nice things about capturing video like this is that the way you can repurpose this. So one of the devices that will be in the John Curtin Gallery is a cylindrical display. So this is one way of capturing material. You can't take a standard video camera and record stuff for that display. So if you record everything in this room, I put the camera in the center and record everything, you can then extract out these other assets from that. So this is a cylindrical projection, and these are the types of displays that you might present that in. And of course, you can do the same thing for a dome environment. Again, you've captured everything, so generating a fisheye is only half of everything. So you can generate an arbitrary number of fisheyes. And this is sort of the eye dome and sort of other opportunities for how you might present this material. The remote operations was around iron ore ship loaders at the Karratha port. And so the requirement here is that the operator needs to see everything that's happening. So the operator is normally sitting out over top of the ship, can look in any direction. And so they're going to put cameras in there. They need that same ability. And doing that with discrete cameras has problems with the operator sort of being able to identify which camera comes after which camera, but also it's not a seamless image. And some of the sports science stuff, which again is about presenting sort of immersive content. Okay, so the last part of the Nantaka story is this cave. This cave is actually where is Nantaka's belly, so they've killed the lizard, and this is his belly. And as per my last shot, the images that you're going to get here are 360 this way and 180. This is a still. The ladybug only captures down to about -140. So this is a quick bit of footage from that. So these are the storytellers over here on this low resolution screen, and this is the dance that occurs while they're telling the story. And this makes it obvious that this is a 360 because as he walks off here, he comes in over here. There's a sort of split here. And this is how you might look at that inside the iDome environment. Sorry about the flashing. That's some sort of interference between my camera and the projector. It's not in the real thing. Of course, an iDome, an environment like this presents you with 180 degrees, and we have 360 degrees. So you can see you can navigate in this environment to look around and concentrate on what you're interested in concentrating on. Okay, so to finish off, another project from earlier this year, as I mentioned, was the, and I haven't mentioned it yet, was the Mameri, which is this remote tribe in Malaysia, West Malaysia. And again, this was a cultural heritage project from coming out of the University of Malaya to record this ritual that they do, which is about healing. So basically, someone in the village gets sick. The priestess, wise woman of the village, goes into a special room, has a dream, imagines what the evil spirit of the sickness looks like, conveys that to a carver who creates a mask of that spirit. They put the mask on the patient, then they perform the ritual, which I'll show you in a minute, around that patient. They then take the mask, put it in the river, and hopefully the patient gets better. So it was about recording both the masks, which, as I've just described, there aren't any in existence because, or the only ones that people have are the ones that have been washed up on some other shore because they get rid of the masks. But also to capture this ritual that they do around the sick person. So I've shown you some panoramic work, and I remember 15 years ago when panoramas were still new, and I would travel the world, and what I'd do, I'd be a real geeky guy and take panoramic photos because that's what was new at the time. And unfortunately, I find myself doing the same thing with 3D. So I travel somewhere and I see an object that I'd like to show my wife. So I take multiple shots, go to the hotel, reconstruct it, and send her the 3D model. So it's kind of, so the new sort of tourist thing. And in fact, it's already happening. There's a couple of initiatives already to build this sort of reconstruction into mobile phones. It won't be as good as you can do if you do it carefully, but that's already happening. Anyway, so this is this dance that they do around a central pillar, which is where we put our camera. And there's this wonderful character who is this guy with his mask who does this dance, which would normally be a dance around the patient. So this is some of the footage. It's really nice stuff. So we capture this 360 stuff, which will be viewed inside probably a cylinder. And we also have a first-person point of view sort of the dance as well. And like I said before, we can repurpose this. So we can create dome versions for it. And this is, again, how you might experience it in the iDome. Okay, so just to finish on. So this hut here is where the priestess does her thing when there's a sick person. There's some herbs and stuff that she takes and puts her into a suitable state to imagine what the spirit might look like. And of course, you're not allowed to go into that room. There's a curse. And none of the locals would go in there, and I totally respect that. Well, I respect it while the locals were there. But when everyone left, I couldn't resist. And the room is quite nice. It's got all these artifacts and this sort of paraphernalia for generating whatever is generated. And of course, my colleagues who were perhaps more sensitive than I was to cultural were telling me I was going to get into trouble for this. And sure enough, I got sick the next day. And this sore throat is 2 months old from that. Thank you.